Hey everyone, my name's Riley Thompson, and I'm a backend engineer at a company in Toronto called Flybits. Today, my presentation will be on exploring the Go compiler by adding some new keywords to it. Okay, so what is our objective today? We're going to add two new keywords to the Go compiler, for loops and unless statements. The goal of doing this exercise is to get an understanding of the Go compiler and how it works, to see some of the code that goes into adding these features, and to look at some of the tooling that the Go compiler provides us. The inspiration for this came from a guy named George Hotz, who did a stream where he added for loops to the C compiler Clang. And just a quick disclaimer before we begin, I hope it's obvious, but I don't think these would actually be good additions to Go. They're just for learning purposes. Okay, so how are we defining a for loop? A for loop is just like a regular loop, except that its post statement is executed 4 times after each iteration instead of just once. So for example, these two snippets of code would produce the same output, 8, 12, 16, and 20. Incrementing by 1 in our new for loop is the same as incrementing by 4 with a regular loop. And what's an unless statement? It's similar to an if statement, but its body is only executed if the condition statement is false. So it's essentially a negated if statement. The unless statement exists in some scripting languages like Ruby and Perl. So these two examples would both produce the same output. Okay, so let's take a look at an example putting these together. The following is valid Go code that prints out whether multiples of 4 from 8 to 20 are divisible by 8 or not. Its output would be this. 8 is divisible by 8, 12 is not divisible by 8, 16 is, and 20 is not. And this code would be equivalent to the following code rewritten to use our new for loop and unless statement. We increment by 4 each time, and then print out whether or not the number is divisible by 8. Note that our increment statement has changed from I plus equals 4 to just I plus plus, since the I plus plus will now be executed 4 times. And our condition has changed from not divisible by 8 to divisible by 8 in the unless statement. Okay, so before we start looking at some of the code, we first need to understand how the compiler works at a high level. The compilation process can roughly be broken up into 3 stages. The first is referred to as the front end, which deals with reading in the source code and direct representations of it. The second is the middle end, where we have an intermediate representation and start to do some optimizations. And finally, we have the back end, where we do further optimizations, some architecture-specific stuff, and actually generate the machine code. The reason we're looking at 2 separate statements today is because we'll see how they can be implemented at different stages of the compiler, one in the middle end and the other in the back end. Okay, so the first stage of the compiler is lexical analysis and parsing. This is when the source code is scanned character by character and tokenized. A recursive descent parser processes these tokens and converts them to a concrete syntax tree. Recursive descent just means that it works top-down, from package-level type and function definitions all the way down to individual expressions. And a concrete syntax tree just means that it's an exact representation of the source code. The syntax tree also contains positional info, such as line and column number, that's used for error reporting and debugging purposes. Okay, so the first thing we need to do in this stage is to add our 2 new keywords as tokens, for and unless. We do this by adding 2 constants with comments, and then using Go's built-in code generation, we generate some of the other code that we need. Before we can start parsing out our 2 new statements, we first need to define the structure of each. These should look familiar to the regular for loop, where we have an initialization, a condition, a body, and a post statement. This structure is reflected in the Go struct on the right-hand side. And this embedded statement struct here is what contains the positional info for things like error reporting and debugging. Okay. Now that we have the structure for our statements defined, how do we go about actually parsing them into the syntax tree? First, we reuse the same helper function that parses out the initialization, condition, and post statement for a regular loop and if statement. And then we recursively parse the loop body. At this point, we're able to parse out the structure of our statement from the source code and are ready to move on to the next stage of compilation, which is type checking. Type checking is done in several phases over the syntax tree, performing tasks such as name resolution, where we map identifiers to objects, constant folding, where we compute compile time constants, and type inference, where we compute the type of every expression and verify that there are no type mismatches. So what does this actually look like in the code? Using our unless statement as an example, the first thing we do is type check the initialization statement. Then we type check the condition and do an additional check to verify that our condition is a Boolean type and throw an error if it's not. And finally, we recursively type check the body of our unless statement. Okay, so at this point, we now have a fully type-checked concrete syntax tree. The final stage of the front end is called IR construction. IR stands for intermediate representation. It's essentially any representation of our code that's better suited for optimization and translation. In our case, we'll be converting our type-checked concrete syntax tree into an abstract syntax tree, or AST. And the Go compiler refers to this process as noding. To do this, we first need to define a new struct that can be used to represent a for loop statement as a node in the AST. This struct should look similar to our concrete syntax tree node. But note that the type of each field is now a more generic node interface rather than a concrete struct. We also need to add a constructor for our AST node, and then again, using Go's code generation tools to generate some boilerplate code. This generated boilerplate code includes things like methods to satisfy the AST node interface. Okay, so at this point, we're fully done with the front end of the compiler, and we can move on to the middle end. In this stage, several optimization passes are performed on the AST, such as dead code elimination, devirtualization, where we convert interface calls to concrete struct calls where appropriate, function inlining, and escape analysis, which is when the compiler determines if a value can be allocated in the current stack frame or if it needs to escape to the heap. And we actually need to make some more code changes to handle escape analysis for our two new statements. First, we do some bookkeeping on the depth of the loop that we're in. Then we do escape analysis on the condition. Then again on the post statement. And finally, we do escape analysis recursively on the body. The next stage of the compiler is called the walk. It's the final pass over the AST before we enter the backend. It's broken up into two steps. The first is referred to as the order step. This is where we convert complex statements into simpler ones and start introducing temporary variables. The next step is called desugaring. This is where we convert high-level language constructs into more primitive ones. For example, range clauses in for loops can be rewritten with an explicit loop variable. This is also where we can implement our unless statement as a negated if statement. To do that, it'll look something like this. First, we do the walk over our condition. Then, we negate our condition by assigning it to itself as a new expression with the condition negated. And finally, instead of returning the unless statement n that was passed into this function, we now return a new if statement that has the now negated condition along with the original body. And that's all that's needed to fully implement our unless statement before we've even reached the back end of the compiler. Okay, now that we're done with the middle end changes, we're ready to move on to the back end of the compiler. Here, the AST is converted to another IR that's in static single assignment form, or SSA. In simple terms, static single assignment is when we split our program up into blocks, where each variable in a block is assigned only once, and each block only has a single branch statement at the very end. Putting our program into SSA is useful because it simplifies our program for us and lets us make a lot of optimizations. Once we have our program in SSA, we first do a series of architecture-independent optimization passes on the SSA form. This includes things like removing unused branches and removing unneeded no checks, and a whole bunch of other things that we'll see a bit later. Another benefit of SSA is that we can now easily represent our program as a control flow graph. In this simplified version of our example program from earlier, we can see how the compiler breaks our program up into blocks that form a control flow graph. We start by initializing main in block 1, and then we move on to the for loop condition in block 2. If the loop condition is true, then we branch to the unless condition in block 3. From here, we'll branch to either block 6 or block 7, where we call F and G respectively. In either case, both blocks then branch to the for loop post statement in block 4. And from there, we go back to our for loop condition. And if it's false, then we branch to return from main in block 5. Okay, so what does the code actually look like to go from our AST to SSA form? The first thing we need to do is create 4 blocks. One for the loop condition, one for the loop body, one for the increment statement, and an end block that will let us escape from the loop. Once we have our 4 blocks initialized, we can start linking them together to create the control flow graph. We do this by first jumping to the loop condition, and then generating the code for that condition block. And then, if the condition is true, we'll branch to the loop body. And if it's false, then we'll branch to the loop end to escape it. Now we can start generating the SSA for the loop body itself. We start by branching to the post statement if we come across a continue, and branching to the end if there's a break. And finally, we generate the actual SSA code for the body recursively. Now we can start generating the SSA code for the post statement. We start by branching to the post statement when we reach the end of our loop body. Note that this is similar to when we branch to the post statement from a continue. And here is where we can finally implement the behavior of our new for loop. We simply generate the SSA code for the post statement in a loop 4 times instead of just once. And fun fact, this means that our for loop could be bootstrapped and implemented with itself after initial compilation. And lastly, we branch from our post statement back to our loop condition, which completes all of the SSA for our for loop. So at this point, we're done with all of the changes to implement both our for loop and unless statement. The final stage of the compiler is machine code generation, where the SSA is lowered, rewriting generic values to machine-specific ones. A series of machine-dependent optimization passes are run that do things like moving values closer to their uses and register allocation. The final output is then passed to the assembler to generate the actual machine code, which will then be linked and then can be executed. Now that we've made all the changes to the compiler to implement both of our new statements, we can use some of Go's compiler tooling to get a better understanding of how things work. To do this, we'll use the Go SSA func environment variable to specify the function we want to generate the SSA for. And in this example, I'm going to disable function inlining with -L to help simplify some of the output. Using the Go SSA func environment variable when building will generate an HTML file that looks like this. Okay, so what we see here is the state of our code at each phase in the compiler. So here we can see the structure of each statement that we outlined before. We have our loop condition right here. We have our loop post statement right here. And we have our loop body here. And then within the loop body, we have an if statement. Why do we see an if statement here instead of an unless statement? This is because our unless statement was implemented in the middle end as a negated if statement, which we see right here with the immediate negation inside the if block. And then of course we have our calls to our functions g and f down here. After this, our program is converted to SSA. Here we can see how our program is actually represented as blocks with single assignment variables. Starting with block 1, where we initialize main. From here, we go to block 2, which is our for loop condition. From here, we go to either block 3, the unless condition, or block 5, where we return from main. Inside of block 3, our unless condition, we either go to block 6 or block 7 to call our two functions. And then each of these will branch back to block 4, our post statement, which of course goes back to block 2, the for loop condition. Now let's take a look at what's going on inside some of these blocks. Starting in block 1, we can see an initialization of a value to 20. And we can see that this value is used in the code in block 2, the for loop condition, with the comparison here. We can also see an initialization to 8 and 0, which are both used in block 3 for the unless condition for checking divisibility by 8. And lastly, we see a value initialized to 1. This is used in block 4, our for loop post statement, where we can see how we're incrementing that loop variable 4 times by the value of 1. Now we'll skip over a few passes and take a look at the SSA from here. A few things have happened now. We've changed how we perform our divisible by 8 check in block 3. It now uses this. And we've also simplified our increment. Instead of having 4 separate instructions, we now have a constant defined as 4 and only need to do a single addition instruction. The next step that we'll take a look at after this is the lowering step. This is where machine-specific instructions begin to get introduced. We start in block 1 by defining constants now with moveQconst. Then, in our for loop condition in block 2, we do our comparison with compQconst. In block 3, our divisible by 8 check now uses testQconst. And in block 4, our addition now uses addQconst. And these are all x86 architecture-specific instructions. The next pass after this is the layout pass. So here, the blocks are rearranged into an order that's more efficient. In our case, blocks 6 and 7 have been moved directly under block 3 because block 3 always branches to either block 6 or 7. The next pass that we'll look at is register allocation. So variables are going to start to be replaced with register values where possible. For example, we can see the AX register is now being used throughout the program in blocks 1, 2, and 4. And finally, the compiler converts the SSA code to assembly code, which we'll take a look at back over on the slides. Okay, so the generated assembly code looks like this. On the left-hand side, we can see the blocks that we've been working with so far are bolded. Note that the instructions for a block are placed above it rather than below it. We start by initializing our loop variable in the AX register to 8 in block 1. And then we jump down to line 7, which is the loop condition for block 2. Here, we check if the AX register value is less than 20. If it's not, then we jump all the way down to line 17 in block 5 to return from main. If it is less than 20, though, we'll continue to our divisible by 8 check in blocks 3. From here, we'll again check the AX value in the AX register, and depending on the result, we'll either jump to line 15 to call G, or we'll continue down to call F. And in either case, we jump back to line 5, which is where we increment our loop variable and then continue back into the loop condition in block 2. And that's everything. So in summary, we saw that compilation can be broken down into 3 stages, each with a different representation of the code. The front end used a concrete syntax tree, the middle end used an abstract syntax tree, and the back end used static single assignment form. We saw how we can implement an unless statement in the middle end by desugaring it into a negated if statement. We also saw how we can implement our for loop in the back end by generating SSA code. And lastly, we saw how to analyze the compilation process and its output with the Go SSA func environment variable. So thanks for listening. If you'd like to take a look at all the required code changes for this, then you can scan this QR code. Thank you.